Hey YouTube, welcome back. So, imagine your application like taking off, like has more users, more data, more everything. But with with this growth comes a critical challenge, which is your database. What once efficient and easy is now quite slow and subtle, and actually is leading to some sort of frustration to your users. In this comprehensive it's not videos, one video, we will deep dive into top 15 database scaling techniques that will equip you with the knowledge to keep your application running alighting fast, to handle massive amount of data, scalable, available, and consistent. So yeah, let's start quite fast. The first thing we will talk about, which is vertical scaling. Vertical scaling, often called scaling up, that's think of it like upgrading your personal computer. When it gets slow, you add like more RAM or faster processor. In this database world, this means beefing up your existing server with more powerful resources. This could involve upgrading the CPU to one with more cores and higher clock speeds, adding more RAM to handle larger datasets in memory, increasing disk storage for growing data volumes, or improving network bandwidth for faster data transfer. If you want to know how to implement it, we can do this like by physically replacing the hardware with a more powerful machine, which is a complete server guide. Or if you're using a cloud provider like AWS or Google, can often dynamically resize your database instances with a few clicks, moving from a smaller instance type to a significantly larger one. You can also optimize the database engine itself by tuning configurations like increasing the buffer pool size in MySQL, which acts as in-memory cache, or allocating more shared memory in the PostgreSQL for similar benefits. Finally, switching to faster storage like SSD, or even in VME drives. I guess they can drastically reduce disk I/O bottlenecks. Okay, but when should we consider to go this solution? Like vertical scaling is, I would say, is a great first step when your workload still fits within the limits of single machine and you prioritize simpler maintenance. It's also beneficial when low latency is crucial and critical, as distributing queries across multiple nodes can introduce overhead. If your application is in its early growth, um, I guess vertical scaling can be a quite appropriate approach. The limitation for this one, I don't know if you understand it, but we only have one server, so we have single point of failure. There is also a physical ceiling to how much you can upgrade a single machine. Even the most powerful cloud instances has a maximum resource allocation. It also present a single point of failure, as I said before. If that one server goes down, your entire database is offline, unless you have a failover mechanism, which add quite complexity to this setup beyond a certain point. The cost of these high-end machines grows like exceptionally. It's huge, making it less economically valuable. Yeah, and also there is something that when you want to do any upgrades, that will require some downtimes, especially in on-premise environments. While simple initially, you'll eventually hit a wall and need to consider horizontal scaling. So yeah, number two, we want to talk about indexing. I guess you thought that I would talk about horizontal scaling, but not now. Like, you have to wait for it. So indexing is a fundamental technique to dramatically speed up database queries. And instead of the database having to scan every single row, in a table to find the data you are looking for, a process that becomes incredibly slow with large tables. An index acts as like a speed dial, which is like basically a speed dial for yeah, a speed dial, or maybe the index in the back of the book. It's a separate data structure that contains a subset of the data organized in a way that allows for much faster lookup. How to implement it? I guess like there is a single column index. Like this is the simplest form, creating an index on a single column that is frequently used in your where. I don't know if you know where, if using SQL, in where clauses for filtering data. For example, if you often users by email, creating an index on the email column can significantly improve query performance to yeah, to a pretty good level. The SQL command for this, I guess you would be like create index like that, but like that, or Gemini. There is also another thing other than the single column index. There is that a composite index. Well, basically, when your queries often filter by multiple columns together, you like you combine them. So there is a composite index on those columns, which can be very effective. The order of the column is the order of columns in a composite index matters. I guess this is something that you need to put in mind, because a lot of people forget that, including me. I did forget this a lot. Okay, but when to use indexes? Use indexing in is quite crucial when you frequently filter or sort data using where or orders by or group by clauses. It's also essential for optimizing join operations as well between large tables, as it helps the database quickly find matching rows. If your application is read heavy, where fast data retrieval is more critical than the speed of writing new data, I guess indexing is a go-to technique. But there is some limitations that you need to know. Like while powerful for reads, indexes come with like a cost on write operations, because every time you insert, update, or delete data, the database also has to update any associated indexes, which is like overhead. Indexes also consume additional disk space, sometimes even more than the table itself. It's important to remember that not every query benefits from an index. Um, if a query needs to retrieve a large portion of table, using an index might actually be slower than a full table scan. Finally, over-indexing, having too many indexes also, this like when you have too many indexes, I guess can degrade write performance without significant improvements in the read at all. Okay, next, cache. Caching is all about storing frequently accessed data in a super fast in-memory layer to minimize trips to the slower database and drastically improve response times. And instead of repeatedly querying the database or for the same information, um, your application can grab it from the cache, which is significantly faster because it's in memory storage. How to implement it? There's multiple ways to implement it actually. There is various caching strategies. There is the cache aside button, which is quite common, where the application is responsible for checking the cache. I guess this is an example of a cache aside as well. On a cache hit, the data is returned directly, and on a cache miss, the application will fetch the data from the database, stores it in the cache for future use, and then returns it to the user. You might use, for example, like a local in-memory caches within your application servers, or distributed caching systems like Redis or Memcached for shared access across multiple instances for web applications. Also, there is can use also content delivery networks, which play a crucial role in caching static content like images, videos, and CSS and JavaScript files. and it stores them at edge servers geographically closer to the users, reducing a load on your origin servers and databases. When to consider using cache? I would say caching is ideal when the same data is requested frequently, such as a user profile, maybe a product catalogs, or the results of common searches. It is essential when you need ultra low latency responses, especially for real-time applications. If your database is struggling with high read traffics, um, caching can significantly offload those read queries, and for web applications, CDNs are indispensable for handling static assets effectively. There are some limitations for that. The biggest challenge with caching is dealing with stale data. If the data in the database changes, the cache needs to be updated or invalidated to prevent users from seeing outdated information. Cache invalidation as well can be complex, with strategies like time to live, write through, or maybe write back, and there even more. Caching also requires additional memory, which is RAM, which can become quite expensive at scale. And since caching primarily optimizes read performance, it's not beneficial for application with a write heavy workloads. Next, sharding. Um, Sharding, also known as data partitioning, it is a horizontal scaling technique where you break down your massive database into smaller, more manageable chunks called shards. Each shard is essentially an independent database containing a subset of your data, of your total data. Yeah. Instead of like one giant massive, as you can see here, we have three. So instead of one giant massive handling everything, the workloads is distributed across multiple servers, multiple smaller ones, significantly improving scalability and performance for very large data sets. How you can implement that? Like you can use like some sort of range-based range-based sharding. Data is like partition based on a range of values of a specific column, like often by user ID or date. For example, users between IDs 1 to 1 million might go to shard 1, and users from 1 million to 2 million go to shard 2, from 2 million, 3 million, shard 3, and go and so on. There is also hash-based sharding, which is a hash function is applied to a key like a user ID to determine which shard the data belongs to. This generally provides a more even distribution, but makes range-based queries more difficult. And the formula might be something like, I guess, shard underscore number equals like hash function modeled by the total shard. There's also a geographic shard, like data is partitioned based on the geographical location of the users. For instance, users in North America might be on one shard while European users are on another shard. This can improve latency for local users. There is directly based sharding as well, which is a separate lookup service or a metadata store keeps track of which shard contains which data when a query comes. When a query comes in, basically, this service is consulted to direct the query to the correct shard. This offers the most flexibility, but introduces another potential point of failure if the directory service isn't highly available. When to consider using sharding? Sharding becomes necessary when your database has outgrown the limits of physical scaling, and a single machine can no longer handle the data volume or query load. It's also crucial when queries on a single table become excessively slow due to the sheer amount of data. If you have high write traffic that a single database server can't manage, sharding can distribute the write load. And if different segments of your users or data can be logically separated, sharding along those lines can make sense. The limitation of shards, I would say sharding introduces significant complexity in managing multiple databases. You have like some sort of like one of the problem which is across shard queries, like queries that need to access data from multiple shards become much more challenging and often less efficient. And also we have a resharding problem, like redistributing data if shard becomes unbalanced or you need to add more shards is quite complex and potentially disruptive operation. And yeah. Okay, next we have read replicas. Read replicas is a technique specifically designed to handle applications with a high volume of read operations, but relatively fewer write operations. The core idea is to create one or more copies of your primary databases, known as read replicas. These replicas stay synchronized with the primary database, but are exclusively used to serve read queries effectively, offloading the read traffic from the main database. So they can be like a master slaves. This can be the master, which is the main, and those could be the slaves that handle all the read operations. How to implement it? I guess the primary database handles. I guess this database, which is a primary one, will handle all the insert, updates, and delete statements, or like all the write operations. Any changes made to the primary database replicated to all the it replicated to all the read replicas. And this replication can be synchronous, where changes are eventually propagated to the replicas. This is the most common approach. Or synchronous, where the write is only considered successful after it has been committed to all replicas. This ensures a strong consistency but can increase write latency. Cloud providers make it easy to set up and even automatically scale the number of read replicas based on your read traffic demands. Applications are configured to direct all write operations to the primary database, but route read queries to one of the available read replicas, often using, I guess, a load balancer to distribute the load evenly. When to consider using read replicas or replication? Read replication is a fantastic solution when your application experience significantly more read traffic than write traffic, which is common in many web applications, content platforms, and e-commerce sites. It helps reduce the query load on your primary database, improving its performance and stability. It can also be used to provide geographically distributed reads, balancing replicas closer to users in different regions to reduce latency. Furthermore, I guess read replicas can serve as backups, providing a degree of fault tolerance. What are the limitations? I guess the primary limitation of asynchronous read replicas is that it has some sort of eventual consistency. There will always be a slight delay known as replication lag between when a write occurs on the primary and when that change is reflected on the replicas. This means user might occasionally see slightly outdated data on read queries. Read replicas don't help with write-heavy workloads, and naturally, more database instances mean increased infrastructure and storage costs. What is next we have? Next we have multi-master replication. So we have 2 masters and we have 4 slaves here. Multi-master replication takes the concept of replication a step further by allowing multiple database nodes to act as both primary for writes and replica for reads, unlike the traditional primary replica setup, where only one node handles writes. Multi-master replicas distributes the write loads across several nodes. So when to consider this? This architecture is particularly useful for globally distributed applications where you need low latency writes in multiple geographic regions. For example, a social media platform with users worldwide might have master nodes in different continents, allowing users to write to the closest database. Reducing latency, I guess. So this will reduce latency. It also enhances high availability because if one master node fails, other can continue to handle both read and writes operation. Furthermore, it can help distribute a very high write traffic that might overwhelm a single master. It has some sort of limitations, like the biggest challenge with multi-master application is handling data conflicts. If two different master nodes concurrently update the same record, a mechanism is needed to resolve these conflicts, which can be quite complex and sometimes lead to data inconsistencies if not managed properly. And the overall system becomes more complex to manage and operate compared to single primary setup. Ensuring data consistency across all master nodes can also introduce high latency. Additionally, every write operation needs to be replicated to multiple nodes, which can increase the network load. Next, we have query optimization. So, query optimization is not about it's not about adding more hardware. It's about making your existing database work smarter, not harder. It's the process of improving the performance of your SQL queries by restructuring them using indexes effectively, as we discussed earlier, and minimizing expensive operations. A well-optimized query can dramatically reduce execution time, lower CPU and memory usage on your database server, and ultimately lead to a better scalability. So one of the things, like examples for that, for example, you need to um, avoid select and star. Instead of fetching all columns from a table, only select the columns you actually need. For example, here select ID, name, and email. So you need all these things only. Also, use query execution plans. Most database systems provide a way to see how they plan to execute your query. So there is explain in MySQL and Postgres works. Analyzing this plan can relieve slow joins, missing indexes, or inefficient table scans. Next, you need to optimize joins, like ensure your columns, ensure the columns you are joining on your indexed. Try to filter down your datasets as much as possible before performing joins to reduce the number of rows that need to be compared. Also, you need to use exits instead of in. For subqueries in many cases, I guess exits can be more performant, especially with large subqueries, as it stops searching as soon as the match is found. Okay, so there's other thing about patch query, like instead of running many individual inserts or update statements, group them into one batch to reduce the overhead of network communication and transaction management. When to consider this, query optimization should be like an ongoing effort, especially as your data grows and queries start to slow down. If you notice like a high CPU or memory usage on your database server, inefficient queries are often the major culprit. Long query response times are a clear indicator that optimization is needed. Furthermore, by making your queries more efficient, you can potentially reduce your database costs, especially in cloud environments where you pay for resource consumption. Next, we have connection pooling. Connection pooling is a crucial technique for applications that frequently interact with the database, and instead of establishing a new connection, to the database every time a request comes in the closing it in sorry, every time a request come in and closing it afterward, which can be resource which can be quite resource intensive and time consuming process, because like connection pooling maintains a pool of ready to use database connections. When your application needs to access the database, it borrows a connection from the pool and returns it when it's done. When it's done, ready for next requests. How to implement that? Like most modern programming languages and database drivers provide built-in support for connection pooling libraries. For example, in Python with like SQL Alchemy and PostgreSQL. PostgreSQL, I guess, called like that. It's a pretty weird name. You can configure the engine of maintain a pool of a certain size. Some database system like Postgres also offer native connection pooling solutions like I guess called PB bouncer. PB bouncer. Yeah, it's called PB bouncer, which acts as a middleware to manage connection to the database server. You configure the minimum and maximum number of connection in that pool. When you should consider this, connection pooling is essential when your application handles a high volume of concurrent requests that require database interaction. If your database server is struggling to handle large number of simultaneous open connection, pooling can significantly reduce this strain. It directly addresses the overhead of establishing new connections for every query, leading to lower latency and increased overall throughput of your application. If you are experiencing slow response times that seem related to database interaction, connection pooling is likely the solution for that. Um, um, what next do we talk about? Vertical partitioning. So, vertical partitioning is a database optimization technique where you split a single table into multiple smaller tables based on its columns. The idea is to separate frequently accessed columns from those that are accessed less often. This can improve performance because queries can only need the because queries that only need the frequently accessed data will be reading from a smaller table with fewer columns, leading to less I/O and potentially fitting more rows into memory. How to implement it? I guess like you identify the columns in your table that are most frequently queried together. These columns are kept in the main table, which and the less frequently used columns, especially those with a large data types like text or blob, are moved to separate tables. For example, these new tables will share the same primary key as the original table to allow you to join the data back together when needed. When to consider this? I guess you can consider the vertical partitioning when you have a table with a large number of columns, and some of these columns are really accessed in typical queries. It's also beneficial when some columns contain large data types that can slow down queries even when those columns are not needed at all. If you have a clear subset of data that is queried very frequently and need to be as fast as possible, vertical vertical partitioning can help with that. It can also reduce the amount of database needs to read from disk or from disk for common operations. I guess one of the limitations that the main drawback of vertical partitioning is that queries that need data from columns in different partition will know how to use join operation to bring the data back together, and these joins can sometimes be expensive and have some sort of performance problem. Okay, where are we? It's a long video. It's a long video. I didn't thought it would be that long, to be honest. So next we have data denormalization. Data denormalization is a database optimization technique that intentionally introduces redundancy into your database schema. Unlike normalization, which aims to minimize data duplication to ensure consistency, denormalization trades some storage space and the risk of inconsistency for improved read performance by reducing the need for a complex join operation. How to implement it? Like one common approach is to add redundant columns to a table that contains data from related tables. For example, in an e-commerce system, instead of always joining the order table with the customer tables, to retrieve the customer's name and email, you might add the customer name and customer email column directly to the orders table. This way, you can retrieve all necessary information for an order with a single query. Another strategy is to pre-compute aggregations instead of calculating sums of average on the fly with every query. You can store these pre-computed values in a separate table that gets updated whenever the underlying data changes. I guess there are some things you need to consider when you denormalization. Denormalization is particularly beneficial for applications that are heavily read oriented and where complex join operations are frequent and causing performance bottlenecks. It can also be useful when performance is absolutely critical and the slight risk of data inconsistency is acceptable or can be mitigated through careful application logic. For example, NoSQL databases often naturally favor denormalized structured due to their focus on scalability and performance for specific access patterns. I guess the limitation for this one, the primary drawbacks of denormalization are increased storage usage due to data duplication and the potential for data inconsistencies if the duplicated data isn't updated everywhere it exists. Next, we have materialized view. Okay, next we have materialized view. Materialized view is essentially a pre-computed and stored result of a query, unlike regular views, which executes which execute the underlying query every time they are accessed. Materialized views store the result physically in the database, just like a regular table. This can significantly improve performance of frequently executed complex queries, especially those involving aggregation or joins. If you want to understand how to implement it, like you create a materialized view by defining a SQL query, and the database execute this query and stores the results, the resulting data sets. For example, you might create a materialized view that calculates the total sales per customer. Subsequent queries that needs this information can then directly query the materialized view, which is much faster than rerunning the aggregation every time. Materialized view also materialized views need to be refreshed to reflect changes in the underlying data. This refresh can be done manually at specific intervals or automatically used to schedule or events depending on the database system. When to consider it, materialized view are ideal for scenarios involving expensive aggregations, complex joins, or time-consuming operations that are executed frequently. They are particularly useful when real-time updates are not critical and slight delay in data freshness. The refresh cycle is acceptable. A huge. This is a long. Okay. So the limitation of this one, the data in materialized view is not always up to date. It's only as current as the last refresh. Storing the pre-computed results requires additional storage space. Number 12, we not much. Okay, we have database federation. Federation is a scaling technique that allows you to integrate and query data residing in multiple independent databases as if they were a single logical system. Instead of aiming all your data into one massive database, you can keep your data distributed across various databases, which might even be different types, and use a federated query engine to access and combine this data. Data federation is useful when your data is naturally distributed across multiple databases due to organizational structures, geographic locations, or the use of different database techniques for different purposes. It can provide unified view of your data without the need for complex and potentially disruptive data migration projects. It's also helpful when different teams manage their own independent databases, but there is a need for cross-functional reporting or data analysis. It can even be used to integrate SQL and NoSQL databases within a single queryable system. I guess it has a limitation like querying data across multiple remote databases introduce network latency, which can significantly impact performance, especially for join that involves transferring large amounts of data between systems. Ah, number 13. Command query responsibility segregation. CQRS. So, CQRS or Command Query Responsibility Segregation is architectural pattern that separate the operations that modify data commands from the operations that retrieve data, which is queries. And instead of using the same data model and database for both, CQRS typically involves having a separate write database, uh, which is optimized for writes, and one or more reads database, which is optimized for reads. How to implement it? Like to the right side command will handle the insert, updates, and delete operations. These operations often result events that are published to the message queue, like Kafka or something like that, which basically will trigger an event, and the read and which and the read side, which is the query model, will subscribe to these events and updates it on store accordingly. This separation allows you to optimize each side independently. For example, the write database might be normalized for data consistency, while the read database might be denormalized for fast querying. When to consider using this architecture, the CQRS is particularly beneficial when your application has significant imbalance between read and writes workloads, and complex joins in read queries are causing performance issues. It also well suited for applications where read heavily outnumber writes, such as analytics dashboards or new feeds. The separation allowed for independent scaling and read and read and write sides. The limitation of it, the CQRS introduced significant complexity in your system. It's awful. It require additional components like event queues and synchronization mechanism and a lot of tests. It's not that easy at all. Number 14, which is data archiving. So first, you need to identify the data that is no longer frequently accessed based on critical criteria like age, status, or specific business rule. For example, you might decide to archive all orders older than 2 years, for example. This data can then be moved to archive table within the same database. If the database system supports partitioning or separate table spaces for archival, or more commonly to completely separate the archive database, or a cost-effective storage solution like a cloud storage like an Amazon S3 Glacier, for example, something like that. Basically, you identify the data archive, you move the data on archive table, and after that, yeah, that's it with you. The limitation for that, like retrieving archive data, can take significantly longer than querying the parameter. This is one of the things that you need to. Lastly, this is really long video. Clustering. Database clustering is a sophisticated scaling technique where multiple database servers are configured to work together as a single unified system. This provides several key benefits, including high availability, ensuring a database remains operational even if one server fails, load balancing, distributed and write workloads across multiple nodes, and fault tolerance, which is like automatic recover from failures. When to consider using it, you can use like clustering in essential for clustering. Database clustering is essential for applications that require very high uptime and zero tolerance for downtime. If your application needs to automatically fail over to another server in case of hardware or server issues, clustering is the answer. It's also beneficial for distributing both read and write loads across multiple nodes, providing horizontal scaling and improved performance under heavy traffic. If you need a self-scaling system that can automatically handle failure without manual intervention, clustering is the way to go. The limitation of it, like setting up, maintaining database clustering, is significantly more complex than managing a single database server. Often requires specialized knowledge and enterprise. It's really hard. I can't even work with it, and I actually spend a lot of time studying system design, but I still find clustering is, yeah, it's really not easy. So finally, video, it was too long. So there, you have it. We have the top 15 database scaling techniques, and I guess in the future I might create a video for each one. As you can see, there is no one-size-fits-all solution. The best approach for your application will depend on your specific workload. If you found this video helpful, please like, subscribe, and hit the notification bell so you'll never miss any videos on the design and data structure. So yeah, see you in future videos.